Let's come up with a formula for the half-life for a first-order reaction. First, let's remember the integrated rate law for a first-order reaction is the natural log of concentration at some time t is equal to minus kT plus the natural log of the concentration at time 0. Okay, so that's from a previous section, just bringing that equation forward. Now, half-life is defined as the time required for 1/2 of a reactant to react. Okay, so the concentration of A at the half-life would be half of the original concentration. We're just dividing it in half. That means that the concentration at time t is 0.5 or 1/2 the initial concentration. Okay, so putting natural log of 0.5 times the initial concentration for the concentration, and then solving for the half-life is what we have on step 2 here. I just want to point out where this division comes from. So if I have the natural log of 0.5 times the concentration of A, 0, minus the natural log of the concentration of A, 0, equals minus K T 1/2. Whenever you subtract natural log, that's the same as division. So that's why here I'm able to divide. Okay. So the natural log of half of the original concentration divided by the original concentration is equal to minus KT half. Okay, half-life. So the concentrations cancel here. We have the natural log of 1/2, which is minus 0.693, and then divide by K to get the half-life, So here's the half-life for a first-order process. Notice that it only depends on K. The rate constant does not depend on the initial concentration of A. Let's also derive the half-life equation for a second-order process. So I have 1/2 of the initial concentration. So this here, remember this was 1/2 the concentration of A at some time t. But we're saying that for a half-life, it's half of the initial concentration. So I've substituted there 0.5 times the concentration of A initially is equal to K times the half-life, T 1/2, plus 1/2 the concentration of A at time 0. And then I just do a little algebra from here to here. Dividing by 1/2 is the same as multiplying by 2. So I put the 2 in the numerator. Okay. And then from here to here, I'm just subtracting 1/A0. So I have 2 minus 1/A0, which is 1/, the concentration of A at time 0, which is equal to K times the half-life. And then solve for T 1/2 by just dividing by K, and I get that the half-life is 1/K times the initial concentration, or the concentration at time 0.